In a flooded Texas pasture, a dark clump spreads over the water without sinking. Look closer, and the clump is alive. Tens of thousands of fire ants. And the way it holds together should not be possible for something made of separate animals. As the flood came up overnight, the colony did not scatter and drown. It gathered. Workers linked legs and jaws until the whole colony became one floating sheet, carrying the queen and the brood dry in the center. A raft like this can drift for days, steering toward higher ground, losing ants off the bottom and rebuilding from the top. No ant is in charge. No ant can see the shape it is helping to build. And yet the raft behaves less like a swarm of insects than like a single strange material. One that pours like a fluid when you tip it, then stiffens like a solid when you press on it. That contradiction is the whole case. By the end, you will see how a pile of blind insects becomes a substance physics still argues about, and why the answer is hiding in the crowd, not in any single ant. The first people to take the raft seriously with instruments were engineers, not biologists. In 2011, a team at the Georgia Institute of Technology, David Hu and a graduate student named Nathan Mlott, scooped wild colonies of the red imported fire ant from roadsides around Atlanta and dropped them, by the thousands, into containers of water. Every time, within about 2 minutes, the loose ball of ants flattened into a floating pancake that would not break apart. They filmed it from above and from the side. They froze rafts solid to lock the ants in place, then put them under a microscope to see exactly how the bodies were joined. What they found was not a huddle. It was a weave. Each ant gripped its neighbors with claws, sticky foot pads, and even its jaws, and the links were not random. They crossed at angles that spread the load, like threads in a fabric. Air bubbles clung to the water-repellent hairs on their bodies, so the whole raft floated on a trapped silver film. And here is the part that sent the study into a physics journal instead of a biology one. What almost no one expected was still coming. For a long time, the floating had been noticed and shrugged off. Farmers across the American South had watched fire ant rafts ride out floods for generations. The ants arrived from South America in the 1930s, and the red imported fire ant, Solenopsis invicta, became infamous long before anyone measured a raft. The easy explanation was that ants are light and their shells trap air, so of course a heap of them floats. Cork does the same thing, and Cork is not a marvel. Skeptics argued the raft was just passive buoyancy. Dead simple physics, no coordination required, nothing a bag of foam beads could not do. Others granted there was some clinging instinct, but insisted the raft was rigid, a fixed clump that either held or fell apart. Both explanations made a prediction. A passive float should not repair itself. A rigid clump should crack under stress and stay cracked. So the Georgia Tech team started pushing on the rafts, poking them, stretching them, dropping weights on them, spinning them in a rheometer, the same instrument used to test paint and molten plastic. The rafts did none of the things a cork or a rigid clump should do. They did something else entirely, and it broke the categories. A raft of fire ants flows like a liquid when you tip it, then turns firm the instant you press down on it. In the rheometer, the same instrument used to test paint and molten plastic, the Georgia Tech team measured exactly that. Squeezed slowly, the raft spread and oozed, rearranging like a thick fluid finding its level. Struck quickly, the same raft pushed back and sprang, storing the energy and releasing it like rubber. The reason is in the grip. Each ant locks onto as many as 14 of its neighbors, and those bonds release and re-grab in a fraction of a second. Pushed slowly, the ants let go and the crowd flows like a fluid. Struck fast, they clamp and the crowd snaps back like elastic. So the raft is genuinely both, a material whose state depends only on how fast you push it. Engineers have a word for that, and they usually reserve it for gels and molten polymers, not living animals. That single measurement is why fire ant rafts are now studied in physics labs that keep no insects at all. And it is still not the strangest thing this crowd does. The result did not stay in one lab. Because a rheometer is standard equipment, other groups could repeat the experiment, and they got the same split personality: fluid under slow stress, solid under fast. Physicists who study what they call active matter, flocks, swarms, crowds that behave like materials, took the raft as a clean test case, and their models reproduced the fluid-to-solid switch from nothing more than local grabbing rules. Then high-speed imaging turned up something the first study had missed. A raft is not static. Over hours, the ants are constantly circulating. The ones on the bottom, pressed against the water, climb up and over to the top, while ants from the top are folded under, so the whole sheet slowly turns itself inside out like a conveyor belt. On average, an ant spends only about 3 minutes exposed on the surface before the churn carries it back under. That rotation shares the danger of being on the wet bottom and keeps any single ant from drowning. No ant volunteers for the turn. No ant is counting minutes. The cycling falls out of the same simple rule: hold your neighbors, climb toward open space, and that is where the case takes its final turn. Punch a hole in a fire ant raft and it closes itself in seconds, with no ant giving the order. This is where the field has quietly settled. The raft is what scientists now call an emergent material. None of its properties live in a single ant, and all of them live in the crowd. Cut it, and ants on the torn edges simply re-grab across the gap until the sheet is whole again. Tip it, and it flows. Press it, and it holds. The same viscoelastic trick, arising with no plan and no leader. Each ant follows a few local rules. Grip whatever you touch, climb toward open space, hold the pile together. And out of thousands of those blind decisions comes a structure that senses load and repairs damage. That is the consensus. The fire ant colony is not just building a raft. It is being one, a single soft machine assembled from live parts. Engineers have taken the lesson to heart, designing self-healing materials and swarms of simple robots that clump, flow, and reform on the same principle. The ants solved a materials problem that human factories still cannot, and they did it with no blueprint at all. No ant understands the raft, no ant can see it, and no ant decides to build it. And yet it forms, every flood, exactly when it must. What else might a crowd of simple things be quietly computing, with no one inside who knows the answer?